Click the bell icon to get latest videos from Ekeeda.
Hello friend, today we will discuss about parallel systems. We will know that how a parallel system works. Then we will talk about the speed up and scale up provided by the parallel systems. Then we will know how the networks on the interconnection based help in parallel system, that is a parallel database architecture of the system. Parallel systems provide the facility of having a better computation time and the I/O processors to have the reduced disk storage as it can be provided with multiple processors. The term parallel gives us an idea where we can give all the tasks that is performing together inside an parallel and multiprocessors architecture. Now we can know that the parallel system not only just reduces the I/O time, but also it improves the computation speed up and scale up for a system. Now when we compute this one as in with a single driver system, then we can know that the parallel systems are better because the sequential access in this single type of system gives us the weightage of the CPU cycle, also wastage of the CPU cycles, and there will be more I/O access than this one. Then there will be a more type of imputation time and also the I/O access to this system. Now, how can we improve this parallel database architecture to the most so that we can have our energy and the computation time stored in for the operation tasks? So that we can done by giving the processor a high number of throughput and response time is responsible for us to perform a large number of tasks to be done in a small time, and also the overhead of each of the processor will be low. Say for an example that there are 10 to the power 12 bytes of data that need to be performed in a single run, then we can run it with the help of parallel systems rather than specifically with a single user or sequential system. Now for the sequential system, when we have to perform the task or divide the task in such a way that one task will be done in this way that the other task can be done after the completion of the task. But the parallel system removed this constriction that now we can parallelly and independently run each of the operations in each of the processors, and finally we can get the result in any of the processor belonging to this one. Now the term throughput and response time helps with this concept that the throughput is the number of tasks that we can do in a specified period of time, and the response time is the time that when the task was initiated in the processor and when it was started by the processor. That means how much time that the processor needs to respond to the task, so that when there will be a less response time, that means our CPU is working great, and when there is a greater throughput, that means the CPU is utilized more and more, because now we are doing by the CPU more tasks at one time. Now, as in parallel processing, we can perform many of the tasks that we can perform in a sequential processing in a specified time. That means the throughput will be higher for in parallel processing. However, there are two types of parallel processing. One is a coarser grained processing, another is a fine grained processing. In a coarser grained processing, we use a small number of large processor where we can run our task. Now first let us exemplify this one. Say when we have a small database that we can perform in two of the processor. Now two of the processor has a size that is more than the average. That means now the processors are considered to be large, so that we do not need a number of processors in it. But how can we define that how many processors do we need to run a coefficiently task? We can do this by dividing the numbers of operations. If the numbers of operations are less, then we can choose a coarser grained parallel processing. That means there will be less number of operations that will be parallelly executed with each other. And say that some of the operations result partially needed by other operations, so we can use also pipeline parallel processing in this type of coarser grained processing. But the finer grain processing needs that larger number of small size processors, so that if there is a large database and on which we need a large number of operations to be performed, say for an example that the selection operation need to be performed on a database which consists thousands of information. So now there are lots of number of tuples that we need to select from a particular predicate. So what we can do, that we can select some of the tuples in each of the processors. Now if we divide the database in such a way among the disks that each of the disks belong to each of the processors, then we can write the task on this processor to accomplish with this disk, so that it can select the portion of the tuple from which the disk is belonging to the processor. So now this is an example of a finer grained parallelism onto the processing of a database. Now these two types of parallelisms are both important in their own demanding area. So the example that we have given, that the small number of large processor and the large number of small processors are dependent on how many operations we need to perform inside a query. So parallel processing is definitely important in inter-query, but also it is important in intra-query. Because inter-query, it can happen that the query are belonging to different transactions and the transactions need to update each other, while one transaction's update can have the impact on other transactions update. But if in an intra-query processing, then we can have inside a query there are much number of operations that we can arrange in a parallel processors, so that we can have each of the processors not being idle at any of the time. Now there are two issues that we can solve inside this parallel processing. One is speed up, another is scale up. Now speed up is a term that we use that if we are increasing the number of times or decreasing the response time according to which the number of processors or the number of tasks can be larger. Say for the n operations are there and we need p processors to simplify this task, then if the task needed to be done in an tn number of time, then we can say that the speed up is, if the previous one tn and now it is go to tm, then we can say that the speed up becomes tm by tn. That means we are decreasing the number of response times or the amount of response time to the increasing number of nature in the operations. So this is mainly known as speed up. And there is another term which is known as scale up. Scale up is the concept of complementary to the speed up. Now in a specified time, if we can increase the number of tasks that can be performed within a processor. Now say suppose that if we have a number of tasks that to be done in p processors within tn time, then we can say if within this tn time, if we can perform m number of process or m number of tasks to be done in m processors, then we can say that the scale up becomes m by n. So in this way we can calculate both the speed up and the scale up and then perform the parallel architecture on this two. Now how we can help the speed up and scale up? Now there are two versions of speed up and scale up both. First let us go with the speed up. Say for example that if the time taken to complete a task in a larger machine is TL. So we can say, what do you mean by larger machine? That means the number of processors are low in this one. So now if we have the larger machine time is TL and that of the smaller machine time is TS. So now we can say from this definition of speed up that the speed up becomes TS by TL. Now we can say that if TS by TL, that is the speed up, which is equals to n, where we can say that the larger machine has n times the resources than the smaller machine. That means now my larger machine has one machine within that the containing information or the resources are n, and the n information can be divided into smaller machines, which case 1 by n of the resources on the larger machine. That means we can say that L equals to n into S. If this relation exists, then we can say that L by S equals to n, so that TS by TL equals to n. So now if we put the speed up inside a graph, then we can see Now we can see the resources and speed relation in this one, that if the resources increase, the speed will also increase. So now we can see that if it is n, then it will be a linear line, or that will call as a linear speed up. So this Ts by TL equals to n, then we call it as a linear speed up. So that is the n resources is the line, so we are having this as n. Now if the Ts by TL is less than n, that means now my larger number of system has less than the n number of resources that a smaller number of system has. So if the ratio of L by S is less than n, then also my Ts by TL becomes less than n, and it is called as a sublinear speed up. And we can use in the graph, like the sublinear speed up is less than n, so it will be this side of the n, and also it will decrease with the number of resources, because we see that the number of resources are less with the L by S ratio. So this is one for a linear speed up, and this is one for a sublinear speed up. Now the same concept goes with scale up, that if we have defined that n by m is the scale up ratio, then by that definition, if we say Q is the number of tasks that we can perform in this Tn number of times, and then if we have Qn, which is n times larger than Q, that means Qn equals to n into Q. So my Qn consists of more number of tasks rather than the Q, which can be subdivided into lesser number of tasks. Now how can we define this scale up ratio? Now the scale up ratio can be directly defined by the speed up ratio, because if we put this Qn, that is a larger number of tasks, that can be done with a small number of time. That means the speed up will be higher to get a scale up. So we can define that Qn equals to Ts by TL into Q, as we know that n is equals to Ts by TL. So now if we can use this definition, then we can see that if Q performed on a machine ML, that means which is a larger machine, now the time taken if it is TL, and Qn, which is performed in a smaller machines, that is n times the larger machines, that means ms, which is equals to 1 by n of mn, then we can say it is Ts. So now my Qn by Q, that becomes Ts by TL. So now we have proved this relation from the scale up concept. This was my relation, that Qn by Q equals to Ts by TL. So now if we put this in a graph, then again we can have two types of similarities onto this scale up and speed up. Now if my Ts equals to TL, that means we are having a linear scale up. That means my Qn and Q are both the same size. So we are not scaling it up at all. So this is the size of Q, and this is my speed up or Ts by TL ratio. Now if Ts is equals to TL, then we call as a linear speed up. So how can we use this linear speed up in the graph? See, this Ts by TL is same. That means it will be 1. So it will be a parallel line to the problem size. Now if the Ts is less than TL, then we call this one as a sublinear speed up. Then what happens, that my Ts is lesser than TL, that means we are actually having a scale up, that for the larger time we are having a less time if we have completed it in a smaller number of machines with a smaller size. So now if it is sublinear, then it will go for the TL side, because the Ts is less than TL. So this one goes in a linear fashion and this one in a sublinear fashion. So by this way we can prove the speed up and scale up within this geometrical graph that we have plotted. Now the scale ups are of two sizes. One is batch scale up, another is transaction scale up. With the batch scale up, the database size increases, and with the increased database size, we can perform all operations in a batch. Say suppose that our database DB is divided into two of the portions D1 and D2. Now what happens, that if D1 and D2 both are given a single processor's P, then it will be a less scale up because we are having only one processor for performing D1 and D2. That goes within TL problem. But if we have, say, the D1, D2 to Dn, which is divided into processors P1, P2 to Pn. That means now we are having an parallel systems with all of this one. Now each of the processors will get a batch of these databases. That means now one processor will get, say, D1 to D3. The P2 will get D4 to D6. Like this way, it will take lesser number of processors for larger number of databases. Now what is the use of this one? Because my database size has grown in a large number of area, then if we try to accommodate that each of the sectors are given a processor, then we may need in a situation where the processor is being less than the database sizes or the disk. That we cannot happen because we know the relation that always D is less than P, that the number of disk will be less than the number of processor. So what we are doing, we are using this batch processing or the batch scale up, where we are batching up the data in some logical reason so that they can be given to a single processor and can perform parallelly execution. The next type of scale up, that is known as a transaction scale up. Now the transaction scale up goes with that when we are having a lesser number of database, now the database can go with different disk. But what we are more transaction with, that are the operations inside a transaction. That means if suppose, say, my transactions T1 has O1, O2 to ON number of operations. Similarly T2 has. So this type of, when we are having transactions with different number of operations, that T1 have N operations, T2 have OM operations, and TK have OL operations. Now as we know that when the database size will be grown, then we can have number of operations or intra operations to be run in parallelly. Say what we are discussing is in parallel execution that can go both for the inter operation and the intra operation. Now what we are having inside the transactions is different operations. Say for an example that if the transaction is to update a database, now that will be the database account deduction and the credit in another database. That means A will be deducted with some amount and B will be added with that amount. Say my transaction has only one operations. Now how the transaction size can increase based on only one operation? Well, it can increase if the number of accounts in the bank large grows. So if AB is less than CD. Now A and B be the previous number of accounts that to be deducted and credited, and C and D are the new number of accounts, then we can say that the transaction size has grown. So then we can use the scale up ratio or by TSTL ratio by including each of the operations and batching up again with the concept of batch scale up, but now is my operations are concerned. So we will not batch the operations, we will batch the databases in a way so that it can be performed in a better and parallel way. That means we can go within parallel systems where all the deductions will be happening in a parallel and all the amount addition will be happen in another parallel. Now what will be the parallel problem in this one? That we need to wait until and unless all of the deductions are completed and this parallel system will become skewed. So what we can do that for each of the processes we are having two accounts with the deduct and the credit account. So in this way we can process the transaction scale up in a better fashion. Now there are a number of factors that goes against this one, that is the against of this parallel system architecture or the speed up of the scale up. The first one is in startup cost. Now how the startup cost is defined, that if we need to speed up and scale up, we need to increase the number of processors. Say suppose first we have P1 and P2 processors, now we need to have P that consists of P1, P2 and Pn number of processors. So there is a large number of startup cost for having the processors. Now if the database size increases with the growth of a demand on the database. So now again we need to increase the number of disks. That means now my disk will consist more number of disks with the relation that m is less than n. Now the second is an inference cost. Now what is an inference? As we are talking about a parallel system, so that it sometimes happens that some operations are partially dependent on another operations. That means there is an inference of one operation inside another operation. So this we need to take care while we are having this parallel system on the speed up and scale up, because inference often just lowered the speed up and also the scale up. So the second point was inference. And the third one means the skew. Now when we have a skew, that means some parallel system that we have the inference problem that happens before one operation is going on, and then we can have a partial result on the other one. Now there are two types of problem in this, that there is a bottleneck while we are having all the transactions or operations that need to be combined. See, for an example, that there are 100 transactions or 100 operations that need to be divided into 10 processors. So this one is number of operations and this one is number of processors. Now we can have as an even distribution with 10 number of operations in each of these processors. But if this happens that some of the processors are having less than 5 number of operations and some of them are having less than 30 number of operations, then there will be a skew while having the bottlenecking condition, because the 5 number of operations processors will be skewed with, while the overfitting of the 30 number of operations inside the processors will face an skew or a bottleneck. Now these problems arises when we can have the speed up and scale up that we need to consider for a parallel system architecture. So now if we can remove this cause by skewing problem, we can use a good hash function or a good evenly distribution range partition function, so that we can have the partition in such a way that both the data and the operations are divided in the processors in an even manner. And also if we can take care of the inference by providing some pipeline parallel processing or some independent parallel processing, then the inference will be much lower. But the startup cost still be there, because we need to introduce more number of processors if we are dealing with a large database with this one. Now we will discuss about the interconnection networks that we can have inside a parallel architecture. Now as we are talking about a parallel system, that means some systems are connected with each other. Now most of these systems are connected via a network, and the network can be of different types. Now the protocol or the rules by which the networks connect these systems can be of many types, but they generally connect the parallel system with 3 of this architecture. First one is in bus, next one is in mesh, and another is in hypercube. Now first we will discuss about the bus architecture. Now inside a bus architecture, there is a backbone network on which every computers or the systems are connected to each other. So now it is very simple to implement and the installation of every system inside this connection, because there is a backbone network which is the network that connects all the computers, and the computers just need to be connected to it. So now if we want to install another mode system inside this network or the processor inside this network, then we can just have this network installed with another computer. But what are the benefits that we have discussed? That it is easy for installation, and also the cost of the startup is low, because now the processors can be easily installed. So there are 2 advantages, but there lies a great advantage. If this system of network fails, then no computer can communicate with each other in any means, because they are connected to the network with this backbone one. Now to solve this problem, the parallel systems that goes with a number of large computers do not use this bus network. So another alternative to this network system is a mesh technology. Now in a mesh technology, what happens that every computer is connected to its adjacent nodes or the adjacent connectors. Now there is no such one network that we can have on which the installation becomes very easy. Now in the mesh networks, as we are having one node connected to its all adjacent nodes, and then it can communicate with each other via these adjacent nodes. Now what happens, installation is not very easy here. In fact, it is rather quite difficult because, say for an example, if it is a midst of a mesh network and now we want to install another system in this network, then it will be extremely difficult for us to do installation this way, because now we need to reinstall all the computers so that the system now we are installing can be fit so that it can communicate with its adjacent nodes. Now in a two-dimensional mesh, as we are having 2, that means 2 into 2, we can have 4 adjacent nodes connected to a single node. If it is a 3-dimensional mesh, then that is 2 into 3, 6 computers or nodes can be connected to an adjacent nodes. Now in this way, mesh technology is a better improvement architecture than over the bus technology, because now if one of the connection network fails, then the connection can be completed with other prototypes or other routes. But in which way that one connectors that is not connected directly with its adjacent node, that means say for a connector A that wants to connect to connector C, which is not a direct connection, then it can pass the message to the route of this B to A. Now let us draw a two-dimensional mesh network first. So now say this computer is having a two-dimensional mesh, that means it can connect to the adjacent 4 computers to each other. Now this one, as being the corner side or the edge side computer node, then it is having only 2 connections as well, this one, and this one. Now let us name this computer so that we can better understand. Say for an example, if my A communicates with B, then it can use this path A to B. Now if there is needed that A want to communicate with F, so there are several paths possible for us. Because there is no direct communication, it can communicate via passing the message to B, which will pass to C, and then it in turn it will pass to F. That means the path A to B to C to F will go for A to F communication. Again, there is another path that is A, D, E, F. So there are more of the passes that can be possible, that is A, D, G, H, I, F, A, D, G, H, E, F. So there are numerous number of paths possible for an indirect communication. And also if the direct communication is there, say for A to B is this path that is not working, that means the network is not working for path A to B. So it can via A, D, E, B connect to it. If it is also working, then it can go to A, D, G, H, E, B. Like this way it can connect to it. But the main problem lies within that if a connector is having 2 of the adjacent node connection that is failed, that means if the A to B and A to D both are failed, then it cannot communicate with any of these 2 paths, because any of the adjacent node path is not working. So the mesh technology's disadvantages, first one is the installation cost or the installation type, and the second one is that any of the adjacent node need to be connect or properly having the network with other connections. Otherwise, the mesh technology of a particular node will fail. Now there is one advantage too in this mesh network, that now that there are many adjacent nodes and there is lesser number of probability to having all the network fails for the adjacent nodes. Now the next type of network that we will discuss is a Hypercube network. Now in a Hypercube network, which belongs to a cube architecture, but with one condition, that one computer can connect to another computer if it is plotted with a binary number and there is only 1 bit difference between these computers. So if they say number 1 computers is having bit 1, another having bit 2, then they can connect with each other. And if there is no connection that is direct between 2 computers, it can be done via the message passing, just like the mesh technology. But here the number of operations on through the response time or the message passing time will be much lesser. Why? Because Hypercube technology, the installation is easier than the mesh technology, because now it is not just connected to the adjacent nodes. If we can connect that there is 1 bit difference, then we can add a node to the 1 bit difference to the existing node on the edge. So there is no need that we need to connect all the adjacent nodes to this computer. It can be connected to the Hypercube in that a way that it differs with only 1 bit with the adjacent node. Now how can we implement this Hypercube? Let us first draw a cube and then see how can one computer can connect with each other. Say suppose I am numbering this as 0 0 0 1 1 0 1 1 0 1. लास्ट वाला डायग्राम कैंसिल कर दो प्लीज़, ये वाला डायग्राम ऐड करो. से सपोज दैट आई एम नंबरिंग दिस वन एज 0 0 0 1 1 0 and 1 1. Now how can they connect with each other? Say that 0 0 can be connected with 0 1 as they differ in 1 bit, again 0 1 with 1 0, again 1 0 with 1 1, but there can be no connection between this 0 0 and 0 0. So introduce this one with another bit, that will be the third bit, by introducing another 0 and 1 here. So now if we put this 0 and 1, so now we can see that every computer, that is this two, differs with each other with an 1 bit, this two also with 1 bit, this two with 1 bit, this two with 1 bit, 1 bit again. So now we can see that it forms a cube with the condition that every computer on these adjacent nodes is having 1 bit difference to it. So as there are 1 2 3 4 5 6 7 8 number of nodes, then we need 2 to the power 3, that means 3 number of bits in each of the nodes. Now the next one, if we want to add to make it an hypercube, then we need to introduce another number of bit so that I can have adjacent with another number of node installation in it. So this type of hypercube is extremely efficient when we are having a large number of database, and then we can have this each of this node contained with a large number of data, and they can be connected with each other. Now the processors that we are connecting with each of this node, or the database that we are connecting with each of this node, can be multiplied in this hypercube because there is only one difference of bit in each of this one. So there is no need to communicate that 0 0 0 to 1 1 0. Now we can do this via this 0 0 0, 1 0 0 and 1 1 0. Now as we are having introduced each bit that is associated and added to the last bit, so there is lesser chance of failure in any of the paths. And if there is also any failure, then we can have the other path to access to. But we need to keep in mind that to 0 0 0 and 1 1 0, we have only this 0 1 0 and 1 0 0 to communicate with. That means first the entire message or the operation need to be copied to this 1 0 0, and then only it can be go to 1 1 0 in this case. So this is an 2 to the power 3 or an 8 nodes that is connected in an hypercube fashion. Now that we have connected with an interconnection network, now the last one we need to discuss about the parallel database architecture. That how a parallel system can get use of a parallel database. Now when we are using the term parallel database, that means in some way we are sharing the database in any of the processor or having the processors each of their copy. So there are, based on this architecture, 4 types of parallel databases. One is shared memory, shared disk, shared nothing, and hybrid architecture. We will discuss each of this architecture now. First we will discuss about the shared disk architecture. Now the shared disk architecture contains all the information that the disk are shared between the processors. That means the database are sharing the disk that they can access to, and all the processors that belonging to this disk now can have their own memory copy. Now belonging to the own memory copy concept, we first need to introduce within shared memory architecture. Now first let us consider the shared memory architecture. Inside a shared memory architecture, all the processors and disks share a common memory. That means there is only one memory or the database that will be shared between the disk. That means the disk can have the partitions, but all of it can access the database in the shared memory, and the processors can also write to this shared memory. So what is the advantage of this shared memory technique? That is, we can have one processors to communicate with another processors just by writing the data into this shared memory, not having the cost of message passing, which incurs an extra overhead to our database on the parallel architecture. Now just by writing or modification by data in the shared memory, we can give the information or communicate with the other processors, because all the processors can see the updates that made by another processors. Now we can differentiate between the shared memory and shared disk, but before that, just infrastructure and look on this shared memory. Say suppose there are 4 processors that is connected to our parallel system, and 3 disks that goes with the database. Now all the processors and the disk share a common memory to each other. Now the memory M can be written by any of the processors one at a time, and now the disk can be shared between this memory. Now what is the advantage that we have described, but the disadvantage is that while one processor is updating the memory, another process needs to wait, because the updation on this one processor on the database can give the anomalous expression, while if 2 of the processors wants to access the database at the same time, or the shared memory at the same time. Now there is one advantage with the shared disk that we have discussed of the shared memory. Now inside the shared disk, each disk copy has its own shared memory, and now the disks can be shared within the processor. Let us first draw the architecture. Again there are 4 processors with us, and now we have 3 disks. Now each of the processors has their own memory. Now using this shared disk, the 2 advantages over this shared memory. The first advantage is that the memory bus bottleneck condition inside this shared memory architecture. That means whenever they wants both of these processors and the disk access to this shared memory, then there will be a memory bus bottleneck, because now all the memory is going to this M shared memory, and there will be a skew because one need to wait for the another to execute. So the term parallel being a little bit confusing in this shared memory architecture. While having, we can parallelly run the processors, but also if there is only one shared memory that the processors can access, now there will be a memory bus bottleneck. And the second advantage on this shared disk is that first, that we do not have the shared memory bus bottleneck problem here, because each of the processors had their own shared memory copy. So now they can update their memory copy, and when this P1 or P1, P2, P3, P4. So when there is P1 updating this M, the P2 can see the update on M while having its own update on it, M. So now there is no problem with this memory bottleneck. And the second problem is that fault tolerance. We call this shared disk architecture a fault tolerant as this shared memory. Say suppose if the memory disk crashes for any reason, then all the processors and the disks will be of no use, as the shared memory is not processing. But inside this, it is more like processor which are fault tolerant, because each of the processors has their own shared memory copy. So inside the RAID architecture, we can see that the fault tolerance is much higher in the shared disk architecture. But with these advantages, there is one more advantage, that the shared disk architecture are sharing the disks too. That means all the disks can be shared this memory as well as with the processor. Say suppose that 3 disks are given with any 3 of the processors, then the disk itself can share their own memory copy inside this shared disk. But the disadvantage that lies within the shared disk is, even if it is free from the memory bus bottleneck condition, but it is not free from the interconnection overhead or the interconnection bottleneck, because some of these processors that are connected to each other must be connected to an interconnection network. So it can be a bus network. As we can see that from the bus we are connecting all the processors and the disks. Even if with the mesh and this hypercube technology, there will be an overhead of this bottlenecking on an interconnection network for the shared disk architecture. Now the next type of architecture is shared nothing architecture. The shared nothing architecture gives the parallel natures at its extent. That means now no memory or no disk is shared between the processors. So each of the processors has their own memory and own disk area. So now if we can implement this one, we will have, so see, suppose there are 3 processors that is attached with our bus network. Now P1 will have its own memory as well as own disk. Same way P2 will have the memory copy and the disk. P3 will also have. Now we can see that the disk references can be found by each of the processors by their local memory. So now it is more efficient on being a parallel one because it is parallel or isolated at its extent. And now we can see it is too much isolated for each of the processors which are not sharing its memory, not as well as the disk. So each of the processors will do their own work in their own part of the database that is stored inside this partitioning on this disk. So now we can store this memory on this P1, P2 and P3, and now we can have each of the memories that satisfies this insufficiency of the interconnection network and the memory bus network. Now there is the overhead of the interconnection network that we forced in the shared disk is much lesser, as well as the memory bus connection network is not at all. That means 2 of these advantages having the shared disk and shared memory is shared nothing concept. But there is one greater advantage is that while we are not having any kind of shared memory, then no processors can see each other's updates. Because they are connected via network, they are more scalable because now the processors can have their memory and disk attached to the computers very easily. Now the network's connection on the intention can have a lesser number of output. So it will increase the throughput on the processor. The final one that we will discuss is an hybrid architecture. Well, the hybrid architecture is a combination of these 3: shared disk, shared memory and shared nothing. Say for the outer one, we are having a shared nothing architecture. Within this, each of the connections, we can have a shared disk or shared memory. Now let us configure and one which we are having a shared memory in the inner one and a shared nothing inside an outer part of this hybrid architecture. So as the outer backbone network, we are having a shared nothing architecture. That means all the shared memory, say S1, S2 and S3 can now have no connections or nothing shared between them. Just only a backbone bus network is connecting them, but no disk memory shared between this S1, S2 and S3. And inside this S1, we are having 3 processors attached to it. This is one shared memory as we have already discussed. Now the processors and the disk can share this memory, but this memory cannot be shared with S2 and S3 memory. So they have their own memory copy. So now my S1, S2, S3 either can have a shared memory architecture or also can have a shared disk architecture. So like the distributed virtual memories where it is conceptually a single shared memory, but logically it is having many disjoint memory systems on which it can have their own shared memory. Also the non-uniform memory architecture where there are many processors inside a single core that can access to their memory and the cores are disjoint from each other. So these 2 are example for an hybrid architecture for having the parallel architecture database. So that is all for the cost, the architecture, interconnection networks and the database systems of a parallel system on the execution of a database. Thank you for watching this video. Stay tuned with Ekeeda and subscribe to Ekeeda. Thank you for watching this video. Stay tuned with Ekeeda and subscribe to Ekeeda.